Good morning again, Physics 20. It is good to see you guys. And we're going to start with our first official lesson via internet. Oh yeah, technology. So what I need you guys to do, please, is I need you to please make sure you guys have this wonderful set of notes that you can see on the screen out. I am going to be writing directly on it using that cool technological thing that Mr. McLeod lent us. And these are the notes that you're going to be starting with are balanced and unbalanced forces. So let's do a wee bit of review before we start. So let's think about what we have with our balanced and unbalanced forces. Now, balanced forces is when all the forces on an object are going to cancel out. So the force of you pushing on something is going to be equal to the force of friction holding that object back. Now, if it's unbalanced, you are going to have a net force, which means that object is going to be accelerating. So if you have a balanced force, you're either stationary or have uniform motion. Key word. Uniform motion, constant velocity, no motion equals balanced forces. If you have an Fnet, you have unbalanced forces. Okay, so you guys remember that from our last lesson on Friday. Sad, last lesson in class. I do miss you guys. So what we're now going to start looking at is how to create force net equations. Now, once again, create them. These are not on your data sheet. We're going to be drawing vector diagrams today. We're going to be labeling our vector diagrams of all the forces acting on these objects. And then we are going to be creating Fnet equations. All right. You guys ready to rock? Come on, more enthusiasm. Okay, that's a little better. So, ladies and gentlemen, as a reminder, our Newton's second law of motion, we use it to calculate our net force on an object. Now, keep in mind, our net force is equal to the sum of all forces. So when we add all forces together, that's our net force. And it is based on our F equals ma equation, or on your data sheet, it's A equals F net over m. And now, when we're going to be determining, well, what actually is our net force on an object when we have a bunch of forces acting on it, well, we're going to have to add them all together to determine our net force. And we can also use that equation to determine the numerical value of our forces. So the first thing we're going to be doing, and yes, you have to draw these for your assignments, is we're going to be looking at creating free body diagrams. Now, a free body diagram is essentially a diagram that you can use to label all of the forces that are going to be acting on an object. So, for example, please put a star here. You are going to need the types of forces that are going to be acting on the object. You're going to need their relative directions. Ladies and gentlemen, force is a vector. It commits crime with direction and magnitude. Despicable Me reference? Yeah? Heard that pun too many times already? Cool. So, we're also going to need our relative magnitude. Now, this is going to be the length of your vector, so the length of your arrow. The larger the force, the larger your arrow is going to be. So, if I draw a teeny tiny arrow, that means we have a teeny tiny force. If we're going to draw a massive arrow, it means we got a massive force. Okay, so other things that we're going to need to keep in mind here, ladies and gentlemen, is we're going to need to keep our X and Y components in mind here, because we are going to have both horizontal forces acting on an object and the vertical forces acting on an object. So that is something to keep in mind. Now, ladies and gentlemen, big star, super important. Your Fnet is going to be 0 newtons if you have balanced forces. So that means it's either going to be stationary or moving at a constant velocity. So highlight that constant velocity, ladies and gentlemen, because I will be asking you questions on your assignment where I say constant velocity, and what that's going to mean, your Fnet will be 0. Lesson subtle hint. Okay. Now, another big, oops, that's not where I write on this thing. Don't write on the touchscreen.
Miss Walker, can you call the front desk, please, Miss Walker?
Okay. Please excuse me, announcement. They need Miss Walker. Okay, so nice star there, ladies and gentlemen. The first of the forces we're going to be looking at is going to be our force of gravity, which we call Fg. You're going to see this on your data sheet as Fg equals mg. We'll be using that equation quite a bit later when we start talking a bit more about other forces. Now, that is going to be your force when, when we drop stuff or when we, throw something up in the air and catch it. Your force of gravity is always acting downwards. Okay, always, always, always force of gravity is down, ladies and gentlemen. That is your direction for down. I guess I shouldn't be dropping this fancy stylus thing. Now, normal force. This is a new force, something we haven't talked about yet. This is the force that is acting in opposition to gravity. It's the force that is exerted perpendicular to your regular force, your force of gravity, perpendicular to the surface. So this is going to be when you push down on a table.
Paulette, can you please call 106? Paulette, call 106, please.
Please excuse me, the announcements again. So when you're going to be pushing down onto a table, the force that the table pushes back up against you is the normal force. Okay? When you just put an object down on the table, it doesn't accelerate through the table because the table's applying a force back on that object, and that is the normal force. Our next, so make sure you get that underlined. We're going to be doing a lot with Fn, so keep that straight. Now, our force applied, ladies and gentlemen, your FAP, as it has become known over the years, so your force applied, or FAP, is, or FAP. FAP is just way more fun to say. This is going to be the force that you're going to exert. This is when you're pushing something, or you're pulling something, you're dragging something, you're lifting something. It's the force that you or something is going to be exerting on that object. Okay? And our last one, something we've already talked a fair bit about unofficially, is your force of friction, or your FF. Now, this guy is going to be constantly opposing motion. So anytime you do anything, any type of movement on the planet Earth, you're going to have friction. So when you're going to be driving your car, the friction will be between your vehicle and the road, the friction of two surfaces moving against each other. If it's going to be in the air, that's our air resistance. That's another type of friction. We're not dealing with air resistance in Physics 20. That's something you will see in future years of physics. For now, we're going to be focusing on the friction between two surfaces as they rub together. Okay. Ladies and gentlemen, if you have any questions with any of this, please feel free to send me an email, message me on Google Classroom. Once again, please do not use my EDU email. Please use my standard GPCSD email, because if you send it to the EDU, I am not going to get it. Thanks. All right, so the next thing we're going to look at, ladies and gentlemen, some examples of how to draw these free body diagrams and how to start making our Fnet equations. So please bear with me. Drawing on this thing is kind of tricky, so I'm going to do the best I can. So when you're going to be drawing your Fnet, your free body diagram, we need the object. I like to draw a box as an object because I'm no artist. You don't have to be an artist to do physics. So you're going to, oops, let me turn the pen tool on. There we go. So you're going to draw a box, and that is going to be whatever object you happen to be dealing with. So in this case, it is going to be a child. This doesn't look like a child, but close enough. And the child is going to be crawling east. So this is the direction of that child's velocity. Now, key thing, constant speed. If you have got constant speed, that means, ladies and gentlemen, that our Fnet equals 0 newtons. 0 newtons. So we have no acceleration. So if we have as constant motion, our vector arrows are going to be the same length. So, because they're going to cancel. So the force applied is going to be in the direction of motion. So that is our force applied. Now, force of friction is always in the opposite direction of motion. So you are going to draw your force of friction opposing motion. Now, you want the arrows to be approximately the same size. I know it's hard to do, but once again, approximate. Okay. Now, let's also think about this child. Is this child accelerating upwards through the air or sinking through the floor? No, because the child is doing neither of those things, we need to have our y-axis vectors also balance. So this guy here, there we go. Normal force is going to point upwards off of that child, and then the force of gravity is going to be pulling the child down. So because the child's neither flying through the air or sinking through the floor, its y motion is stationary, your y vectors are going to be the same size. Now let's build our Fnet diagram. So let's think about the sums of these guys. Now once again, we always have to keep our x and y components separate. So our Fnet on the x is going to equal our force applied. And once again, this is the sum of all forces. Your force net is the sum of all forces plus, there we go. I'm trying my best here, guys. This is really hard to write on. Plus, however, let's look at our direction for that force of friction. That direction is going in the opposite direction of our force applied. So that means it must have a negative value. So plus the negative force of friction. Okay, so that is our Fnet on the x. Now, because the Fnet on the x is going to equal 0, I could always rewrite this guy, okay? So a little bit. We'll just add a next piece over here. So the sum of each of these guys is going to equal 0. Let's see if we can get this to right. There we go. Okay, so our Fnet is going to equal 0. So that means our force of friction, force applied, have to have the same numeric value. Okay, let's look at our on the y. So this is not one to go, there we go. Our Fnet on the y is now going to equal the sum of the forces on that y-axis. So we are going to be, once again, you can pick whichever one you want to be positive or negative. I like it to make down negative when I've got both an up and down motion. So I'm going to make normal force positive and force of gravity negative. It doesn't have to be that way, but that's how I'm going to do it for this question. So my normal force plus my negative Fg. So normal force going up, positive direction. Fnet is the sum of all vectors, the sum of all forces, and that direction for your Fg is down, therefore it's negative. All right, there, ladies and gentlemen, is our first example. Let's look at our next example here, where we have our toy car rolling north across a carpet after a child has pushed on it. This is a key entity right here. Now, where's my pen? Come on, pen, you can do it. There we go. So I'm going to draw a toy car. Close enough. Now, key thing, after a child has pushed on it. Come on. The motion of the car is going to be this way. Okay, that's where this car is going. It is going to have a force of friction. Absolutely. And we always have friction when we have motion. Okay. However, ladies and gentlemen, the child is no longer actually physically pushing the car. The kid has pushed it and let go. We don't have a force applied here, ladies and gentlemen. There's no force being actively applied to that toy car. So we don't put a force applied there. There is no longer a force applied. Its momentum is carrying it forward. So we still have our normal force on that car, and we still have our force of gravity. Sounds good? All right. In this case, for when we get to our Fnet diagram, our Fnet equation, excuse me, it is now for on the x value, your Fnet is only going to equal the force of friction. That's the only force that's actively acting on that car right now. Now, when we're going to be looking at our Fnet on the y, it is going to equal the same as our previous equation, our Fn plus our negative Fg. Can I actually write over top of my thing? No, I can't write over top of my little video thing in the corner. There we go. Now I can write on it. Pen button. And close bracket. Sounds good. So here, our Fnet, we are going to have an actual value for our Fnet. It's just going to be in the same direction as our force of friction and opposite direction to our force of our motion. So this guy, once again, because our forces are balanced and we are not accelerating, your Fnet on the y is going to equal 0. Sounds good? Awesome. All right. Next thing we're going to do is we're going to look at how to do some calculations with this here. So we have a few calculations, and then I'll give you guys an opportunity to pause the video and then go and do some practice problems. Sounds good? All right, let's look at some of these practice ones. So Fred is pushing a piano. Oops, he doesn't like that. There we go. All right. Hey, come on. What are you doing? There we go. Sorry. Fighting with the technology. Woohoo. All right. So Fred is pushing a piano along the floor at a constant velocity. Ladies and gentlemen, the second you see that word, constant velocity, that means your Fnet is 0 newtons. Okay? With a force of 250 newtons. Okay, so if Fred is applying the force, that means the information that we have is our force applied is 250 newtons. Okay, so let's think about this for a sec. Let's draw a Freebody diagram. That's always going to be our first thing. There's our lovely Freebody diagram. Piano. It works. And now we have a force applied. We have a constant velocity or constant speed going this way. And now the thing we need to think about is our Fnet equals 0. We absolutely have a force of friction. Okay. And ladies and gentlemen, they're going to be the same length. Because Fnet equals 0, okay, because we have that constant velocity. You are also, it's a good idea to draw our normal force and our force of gravity. I'm really hoping your guys' writing is going to be neater than this. It's really hard to write neatly on this thing. Okay, so we have our kind of messy Freebody diagram. Our next step, once we have our diagram in place, is going to be to build our Fnet equation. So my Fnet is going to equal my force applied plus my negative force of friction. So we've been asked to calculate our force of friction. And so, ladies and gentlemen, let's put some numbers in here. Our Fnet, which we learn from that word constant velocity, is 0 newtons. So what this means, once I erase that, is that I'm going to replace my Fnet with 0 newtons. I'm going to replace my force applied with 250 newtons. And it's going to be the equivalent of minus my force of friction. So, ladies and gentlemen, I am now going to rearrange this, and I am going to add my force of friction on this side. Okay, so once I add my force of friction over here, add force of friction to 0, that's just force of friction, I am then left with 250 newtons, ladies and gentlemen. So my force of friction is equal in magnitude to that of my force applied. We could even rewrite our equation of your force applied is going to equal our force of friction. Now, ladies and gentlemen, force is a vector, so I'm going to need to add a direction here. So because my force applied is going forwards, I am then going to make my force of friction have a direction of backwards. Sounds good? All right. So that is our first question, and that's how you're going to handle your net forces of 0, is when you have a net force of 0, it means you have balanced forces, and you can equate those two forces to each other. Okay. So let's look at our next video here. Next question here. And let's see what we got. I got the pen tool. There we go. So a 428 Newton applied force. Okay, so I'm going to list out what I have is 482 newtons. Causes a car to accelerate. Ladies and gentlemen, when we say accelerate, this tells us we have a net force along a horizontal road. So our direction is to the right. And the net force acting on the car is 152 newtons to the right. Okay. So my Fnet is 152 newtons to the right. What is the force due to friction? So ladies and gentlemen, because we have the keyword accelerate, we have a numerical value for net force, our forces are unbalanced, we are going to draw our free body diagram. And yes, ladies and gentlemen, when you are thinking of this question, do I have to write my free body diagram on my assignment? Yes, you do. If you do not write your free body diagram or draw your free body diagram on your assignment for all of these Fnet questions, you lose a bunch of points. So draw your free body diagrams, ladies and gentlemen. Okay, so there's our object. Now the car is accelerating. So that means its force applied is going to be significantly larger than its force of friction. Okay. I'm also going to add my normal force and my FG. Okay. So now, ladies and gentlemen, looking at our force of friction and our force applied, we can clearly see by the size of those arrows that this is obviously a larger force applied than we have force of friction. So now I am going to draw and write out my Fnet equation. So my Fnet is on our horizontal here is going to equal our force applied plus our negative force of friction. That should say force of friction. Let's get that fixed. There we go. Okay. So let's rearrange this, ladies and gentlemen. We are trying to isolate for our force of friction. Okay. Keep in mind it's going to be negative, so this is going to make things a little bit trickier now. I can't just simply add it over. Okay. So what I'm going to do to rearrange this is I'm going to subtract my force applied, which will cancel this here, and then I will subtract my force applied on this side. Okay. Okay. Notice I kept that negative sign. Don't forget to keep that negative sign, ladies and gentlemen. So I'm going to adjust our screen a little bit so we can continue to see what's happening. Okay. And now I'm going to put my numbers in. So my negative force of friction is going to equal my Fnet of 152 newtons minus my force applied, which is 482 newtons. And my negative force of friction, ladies and gentlemen, is going to give us an awesome value of negative 330 newtons. Notice the two negatives on that side there. So with the two negatives, I am simply going to cancel those out. There we go. So I'm going to wind up with 330 newtons. Now I'm going to need to think about the direction I need to give this, because forces are vectors. I want magnitude and I want direction. So for this guy, I am now, for my final answer, I'm going to make sure I've got the right sig digs. When you go back and look at the question, I've got 3 sig digs, so I am good there. And 330 newtons. It's opposite to the direction of motion, so therefore my direction is going to be to the left. Box your final answer, ladies and gentlemen. So that way, I know that's what you want me to mark. Okay. So ladies and gentlemen, my advice at this point is to pause the video. You guys have definitely listened to me natter for long enough now. So pause the video and then go and do the questions at the bottom of the page, or at least some of them in your workbooks, until that way you're comfortable with doing some of these. And then start the video again, and we'll go on to the next piece. All right. So, going to, now that you've had a chance to do those questions, you've unpaused your video, we're going to look at some increased difficulty with some of these questions. So we've got, let's see, questions 3, 4, and 5. Now, some of these are pretty big questions, so bear with me here. Okay. So for number 3, a 12-kilogram object is pushed with a horizontal force. So keyword horizontal force, that's what we're going to be focusing on, of 6 newtons east across a horizontal table. Now we have the mass, so keep that in mind, that's also important. If the force of friction between the two surfaces is 2 newtons, what is the acceleration of the object? All right, let's list out what we have. Mass of 12 kilograms. Now, when we say a horizontal force, or pushed with a horizontal force, that, ladies and gentlemen, is our force applied of 6.0 newtons. And it is going to be going east, okay? And we also have a force of friction of 2 newtons, and we've been asked to calculate the acceleration of that object. So let's think for a moment under our Freebody diagram. We've been asked to calculate the acceleration of the object. We have a larger force applied than we have a force of friction. So that means I'm going to draw my force applied here, and I'm going to make it significantly larger than my force of friction. We are neither accelerating upwards nor accelerating downwards. So my Fn and Fg are going to be the same. I'm going to focus on our horizontal motion here. So I'm going to build I need to build an Fnet equation. Now let's think. I've asked you to find acceleration. Think about it. How are you going to find it? Fnet equals ma from your data sheets. And with Fnet equaling ma, with the sum of these two forces, can you find Fnet? Yeah, you can. So there's a couple different ways you can do this. You can make one big equation, which is what I'm going to do to solve this, or you can find your Fnet, then plug that into Fnet equals ma. So we're going to start by building our standard Fnet equation. And it's going to equal my force applied minus my force of friction. Now, I'm going to write this in a simplified version than I did on the previous questions because plus a negative is the exact same as minusing something. So it's just easier to write force applied minus force of friction instead of force applied plus negative force of friction. Mathematically, same thing. Okay. Come on, computer. Here we go. So my force net, ladies and gentlemen, is also equal to mass times acceleration. So MA is going to equal my force applied minus my force of friction. Guys cool there? Okay. Now I need to find my acceleration. So I'm going to divide out that mass. So I divide by the mass on one side, and I divide by the mass on that side. Just going to scroll down a bit here, guys. There we go. So I'm going to have my acceleration is going to equal my force applied minus my force of friction divided by the mass. I'm going to plonk my numbers into my equation here. So I'm going to have acceleration is going to equal my 6 newtons minus 2 newtons, and I'm going to divide that by my mass of 12 kilograms. Watch your brackets when putting this into the calculator, ladies and gentlemen. Either do the math initially and go 6 minus 2. Oh, that's 4. Divide that by 12. And then get your answer. Or bracket 6 minus 2. Bracket 12. Enter. You put it into the calculator wrong, you're going to get the wrong answer. Watch for that. Okay. All right. Equals your lovely value of 0.33 repeating meters per second squared. So ladies and gentlemen, I need sig digs. I'm just going to scroll down a bit so I can actually write and not write on my face. There we go. All right. So with this, I need my appropriate number of sig digs, I need units, and I need direction. So when I come back to my question, I see that I have a grand total of 2 sig digs. So I want to write this as 0.33 newtons. Let's try that again, shall we? I would deduct half a point from myself for that. There we go. Meters. Come on, computer. Second squared. And my direction is going to be to the east, ladies and gentlemen, to the east, because that's the direction that the car is moving. Okay, so underline or box your final answer so I know what you want me to mark as your final answer. Help me help you get the most points possible. Show you work. All right. So ladies and gentlemen, that is our first question there, where we're then going to be finding acceleration. Okay. What I would do if I was you, pause the video, try this question on your own, and then come back to it. Okay. Pause. Do the question. Okay, you've done the question now, and now I want you to check your answer with how I do this question. So I'm going to go through this one a little bit faster than I did the previous one, because I'm assuming you've already done it, and you're going to now just check your answer. Cool. All right, so I'm going to start out by selecting the pen tool, and I'm going to read my question and list out what I have. Well, I have a mass of 20 kilograms. It's pulled horizontally, a level floor with an applied force of 27 newtons north. Okay, so we're going north now. So my force applied, 20 newtons. We're going north. The object is accelerating at a rate of 0.8 meters per second. Squared, excuse me. Need to get my units correct. And then you've been asked, what is the force of friction? Okay. So I have everything listed out, and I'm going to draw my free body diagram now, which you need to do for pretty much every single one of these questions, ladies and gentlemen, if you want to get full points. So my velocity is going in this direction, and it's going north. And this is going to be my force applied and my force of friction. Let's look at this diagram for a moment, ladies and gentlemen. What would I be deducting points off myself for? You're right. My force of friction arrow is too much the same size as my force applied. I can't tell the difference between them. It's not obvious that one's bigger than the other. To me, it looks the same. So therefore, if you draw your vector diagrams like this, you're going to lose points. I have to obviously see when an object is accelerating that those arrows are truly different in size. So I'm going to fix that. And now I'm going to have my force of friction significantly smaller than my force applied. Okay, I'm going to draw my y forces because I can. They're going to be equal in size. I now need to build my Fnet diagram, my Fnet equation. Okay. So I have my basic Fnet diagram, my basic Fnet equation. And now my Fnet, according to Newton's second law, is mass times acceleration. So I replace that Fnet with ma. And it's still going to equal my force applied minus my force of friction. So in this case, what you should have done is looked at what you have and figured, well, I have mass, I have acceleration, I can put those in there, and then I have my force applied. I'll just rearrange all this to solve for my force of friction. Cool beans. So now I am going to, well, we got adding happening here, so I'm going to subtract out my force applied from both sides. Okay, I'm just going to scroll up a bit here so we got some more space to write. Okay, and then so my force applieds are going to cancel, and I am going to have ma minus my force applied is going to equal my negative force of friction. Okay, so I'm going to put my numbers in now. So my force applied is 20 newtons. And let's try this again. There we go. I have to do MA first. Come on, computer. There you are. So my mass is 20 kilograms. My acceleration is 0.8 meters per second. Watch your bed mass here, ladies and gentlemen. And then we minus our force applied, which is 20 newtons. Okay, I'm going to scroll up again here. Okay, and you're going to wind up with a negative force of friction, which is equal to our negative 11. Now, once again, negatives on both sides. Let's get this fixed. 11 newtons. I come back to my question. I'll look at my sig digs. Well, I've got 3 sig digs, ladies and gentlemen. Do I have 3 sig digs? No, I've got 2. 0.8 meters per second squared, ladies and gentlemen, is 2 sig digs. So 11 newtons is fine. And now I need to think of my direction. The vehicle was originally traveling north. Friction always opposes motion, so friction is going to have a direction of south. You're going to box your final answer. Okay. And once to show that that's what you want me to mark, and full points. Oh yeah. Okay. I keep wanting to say, any questions, ladies and gentlemen, expecting you guys to answer, but no, I'm sitting in an empty classroom talking to my computer. Kind of depressing, actually. I do miss you guys. Okay, so let's look at our last question, and then that'll be the end of the lesson. You guys will have some chances to do some more practice problems, and then you can start chipping away at your assignment with the questions that you guys know how to do. Okay. So, ladies and gentlemen, last question, of course, the trickiest question. My advice, once again, give it a try, see how you do, pause the video, and then come back and watch this once you've tried it, and then we'll go over it. So, complete the question, pause the video, show your work, units, and sig digs. Okay, you've done the question. You've paused the video. It obviously takes you more time to do it than me, the time I spent being silly. Okay, so ladies and gentlemen, we're going to go through this once again a little bit quicker because I've assumed you've paused the video and done it, and now you're just checking your answer. Okay. So, a 64-kilogram baseball player is running to home plate when the baseball player is 2.35 meters from home plate. Okay, let's listen to what we have. Mass is equal to 64 kilograms. He is 2.35 meters from home plate, ladies and gentlemen. She slides to a stop. Stop. That means our VF is 0 meters per second to make a safe play. If 895 newtons of frictional force was applied, so force of friction is 895 newtons, acting on the player as she slides to the home plate, what was her initial speed when she started to slide? Oops. Not 0. What's question mark? There we go. All right. So this is a pretty tough question. First thing you should have done is you should have drawn your vector diagram, a lovely free body diagram. So, ladies and gentlemen, we still have our normal force. We still have our FG. We have force of friction acting on the baseball player as she slides. But the key thing is she slided. She has dropped to the ground and slid to home base. She is not applying a force to herself at that time. So just like that car question where the kid pushed a car and when it wasn't actively applying a force on it, it had no force applied. This baseball player, she's got no force applied. So that means we are going to add our, so that did not show up very nicely, direction of motion going this way. But now our Fnet diagram is going to be a lot easier. Our Fnet equation is going to be equal to our force of friction. On the X, the only force that's acting on her at this point is the force of friction. So that means my F force of friction is going to equal MA. Pretty good, eh? Not too shabby. So next piece we need to think about, scroll down here so we got more space. Yeah. Is I can find acceleration here. I don't have acceleration yet. That's what you gotta find, ladies and gentlemen, is your force. Let's try this again. It's your acceleration. Once you have your acceleration, you can look at your data sheets and then you can pick an equation that we used in our first unit to help solve our problem. It has to be an acceleration question. If you use V equals D over T, I will cry inside because this is accelerated motion, not uniform. Okay, so we have our mass and we're going to divide out mass. So acceleration is going to equal our force of friction over mass. And our acceleration is going to equal our 89 divided by your, come on, computer, don't do this to me. There you go. 64 kilograms. Okay. Put that in your calculator. You are going to get the lovely value of your 13.9843 ... meters per second squared. So let's stop here and think about this for a moment. Ladies and gentlemen, my Fnet is equal to force of friction. What direction is that going in comparison to my motion, my speed, my velocity? What direction is that going in? Opposite. It's going to be negative. So what you got to do, ladies and gentlemen, is we need to make this negative. This is going to be a negative 13.9843 because she's slowing down. She's got negative acceleration. Okay, so you have to make that negative. If it's not negative, you're not going to get the right answer. Okay, you then are going to need to pick an equation that's going to allow you to calculate your VI. Well, we have VF, VI, A, and D. Your best equation is going to be your VF squared is equal to VI squared plus 2AD. So I need to rearrange to get my VI. We're adding here, so I need to subtract my 2AD from both sides. And now VF is 0. We're stopped.
Yeah, the EA is doing the lockers. Come to the library for
announcements.
A moment, please. EA is doing the lockers. Could you come to the library for a moment, please?
Okay. Announcements are over. We continue. You know how much I love announcements. Okay. So VF squared is 0. So that means when I subtract 2AD from that side, I get negative 2AD is going to equal VI squared. This is where it becomes very important, ladies and gentlemen, to make sure you have that A is negative. I'm just going to scroll down so I'm not writing on my face. Okay. So, select pen tool. All right. So we have your VI is going to equal the square root of negative 2AD. I think you guys are seeing the problem. We're square root of a negative. We can't do that. Yes, you can, because our acceleration is negative. Okay. So your VI is equal to negative 2 with your negative 13. Oh, come on, computer. There you go. 13.9, etc., etc., etc. Use all values. And your distance, we're going to have to go all the way back up here to get our distance of 2.35 meters. All right, I'm pretty sure I can write off the side here. Yeah. Okay. Then I am going to square root the lot. Notice because that negative 2 there and that negative 13 are both negative, a negative times a negative is positive, so therefore we can square root that. So if you forget to put your direction in your acceleration, your calculator is going to freak out and say, error, you can't do that. So direction does matter, guys. It really does. Okay. And then once you put your numbers into your calculators, running out of space, you are going to have your VI is going to be the wonderful value of 8.107 ... All right. So I need to look at my sig digs. So I go all the way back to the beginning of the question, and I have 3 sig digs. So I'm going to go 8.11. It's velocity, so it's meters per second. Now, the question says her initial speed, not velocity. So because it says speed, do I want direction? No, it is scalar. Scalar equations do not get, or scalar entities, I should say, do not get direction. Okay, so that is my final answer. Okay. Whew. Long question. So ladies and gentlemen, that is it for this particular lesson. At the bottom here, you guys see you've got your practice problems for you to work on. So please give those a try, and then you'll be able to go and chip away at the questions on your assignment that you guys know how to do after we've done this. And if you weren't able to follow up with Keep With the Notes, if you go on to your Google Classroom, you will have the link where all the notes are already written down. So I hope that helps. And ladies and gentlemen, it's been a pleasure. We will talk to you guys on our next video, and rock the physics. I think it's showing up backwards on the video, isn't it? I think it is. Sorry guys, I can't write in mirror. So see y'all later. No fires, injuries, or explosions, ladies and gentlemen. And how do I stop this thing? Where's my stop button? You guys know me in the technology. We'll be here forever while I figure out how to stop this. Yeah, man. Doesn't want to stop. All right, guys. See you next time. Have a good day.